Hi everyone. We meet today to talk about removing stuff, and we're gonna talk about a well-known idiom for most people in the C++ industry, but we're gonna approach it from a totally different angle, and we're gonna discuss about the problems that people face when using this kind of stuff day to day, starting from experienced engineers casually using this because they're comfortable and it's a well-known idiom, and to people learning stuff for the first time and struggling to get around the gotchas and trying to understand the rationale for doing stuff the way they've been told, the way they've been taught. So right from the start, I would say this discussion would be no discard love story. And if you're not familiar with the fairly recently added attribute to decorate functions and even structures, I do encourage you to take a look at the advantages it tries to offer and the tremendous benefits that you might gain in correctly adorning your APIs, your public interfaces with such attributes. So I'll start with a case study, and it all involves upgrading a compiler toolchain. And this happened a few months back as part of the revamp of the STL library in MSVC. A bunch of functions have been decorated with this no discard attribute when compiling in C++ 17 mode or newer. And mind you, this is not a standard requirement. So this effort was done by the Microsoft STL library team to mark over 3,000 functions with no discard attribute, with the specific purpose of catching such issues and misuses of the APIs. And as always, compiler toolset upgrades can be a hassle, but as it turns out, in this case and others, can uncover quite a bit of problems. And in the end, although it is a non-negligible effort, it will pay off. So as soon as we upgraded to the particular revision that shipped this modification of the MSVC STL, and we recompiled the code, all of a sudden, a bunch of new warnings started to pop up in our code, where we were using various STL functions and the return values were discarded. And some situations were, let's say, warranted, but the most troubling bit was that we uncovered a whole bunch of situations where STL APIs were misused and their return values were thrown away, and even situations where developers were clearly confused about the way those functions were supposed to be used. And I want to emphasize that at the time, and currently we're still using, we're doing cross compilation, and we're using alternative STL implementations as well for testing purposes. And such scenarios will not be visible if you're using lib C++ or lib standard C++, because as I told you, the standard does not require implementers to use don't discard for those functions. So what did we uncover? I'll say it starts with a simple task. Let's say we have a bunch of items in a collection, and the simple task at hand is to remove certain elements matching a given predicate. Sounds like a fairly trivial task. Of course, real-world examples are tend to be a bit more convoluted, but the gist is just the same. So what do? We write a quick for loop, like any 10x engineer would do? No, we're much more experienced than that. Of course, we're gonna use the algorithm collection in STL. And first algorithm that comes to mind is remove or remove if. If we're gonna be fancy and use lambda functions. And this was the case for the troublesome warnings that I mentioned earlier. We discovered a bunch of situations where this algorithm was misused. People using it apparently were confused about the way it was supposed to work. And the fact that we discovered it was due to the fact that it was now marked as no discard in the STL implementation. And basically, in some scenarios, not a lot, but in some scenarios, this algorithm was used directly with the expectation that the algorithm will remove something from the given range. You might ask, didn't have unit tests, and if we did those unit tests, those unit tests, why were they passing? It wasn't that as bad as that sounds, but it wasn't good either. So the whole discussion about the proper coverage and robustness of those unit tests would be subject for entire new presentation. But fair to say that we were worried about the results that we uncovered, and in some situations, the observable errors from this misuse of the API sort of was latent, and in some situations even harmless, but certainly not the intended behavior. So definitely action had to be taken to correct those. And I'll talk more about ways to remedy this kind of stuff. Of course, the missing ingredient here was erase functions from the actual collection that was used, let's say vector. And this was the forgotten piece of the puzzle. Just to recap, for people that are maybe not familiar with the details of how things are supposed to work in STL, these operations are disjoint. The remove algorithm is disjoint from the API, the function that actually does the erase from the given container for reasons of abstracting away the remove algorithm from the collection that it can operate on, a staple design choice of the STL implementation where we separate the algorithms and move them higher up in abstraction from the underlying containers that they can operate on. So remove moves the elements around based on the given predicate, in the case of remove if, and it returns a past the end iterator for the new range of values, sort of this pictogram I try to show here. And the important bit is that it does not change the size of the container. So if we have remove if with a simple predicate like this one, and we ask people, how do you think this works? A common answer is that remove if moves all the elements you want to remove to the end of the vector, and then you come with the erase function from vector, let's say, and you get rid of those elements. I was surprised that I was not surprised to find this intuition for people new to the STL or new to C++, and how it works. I was more surprised that this intuition also came from more seasoned C++ engineers, which is even more troublesome. And that's why I think it's important to educate people in the details and spread this thing as wide as we can. So this is clearly wrong. And this isn't what remove if algorithm does. If it did that, it actually would do more work than necessary. And it would actually be a partition instead of remove. What remove actually does is to move elements that won't be removed to the beginning of the collection. So the algorithm cares about the elements we want to keep. It doesn't move the uninteresting bit to the end. So seems like complementary, but it's not. It really makes a difference. So if you really think about it, what you get at the end there is garbage. So you might have moved from values, you might have duplicates, basically anything in there is supposed to be considered garbage, and you shouldn't touch those values. So remove moves the interesting or the elements we want to keep at the beginning, and returns an iterator at the start of the garbage range that we need to trim off using the erase companion function. So this is the bit that most people get wrong. So before erase is called, we have some garbage there, and after erase, we are left out with the interesting elements, the stuff that we actually wanted. So that's why it's called the erase remove idiom, because you have this dance between calling the remove algorithm and right away consuming the return value and passing it into the erase function as a start iterator. And this is where the no discard attribute comes into play. Some people were confused and thought that just calling remove might be sufficient. But there's one more gotcha here, not just because most experienced engineers actually know to use this idiom as an atomic operation. It's combined all in one. So they're very familiar to this site of erase remove. But there's one more gotcha here. And it's related to this last iterator here, the container end that we must supply in. And the problem here stems from the fact that erase is actually an overload set. And there's one more erase that takes a single iterator and is supposed to erase the element at the given position. So if by some chance a developer will forget to add that v.end highlighted in yellow there, you will silently select and erase the wrong thing, because you will select the erase function with a single argument, and you will delete just a single element from the vector, and that was clearly not your intention. And it's a very forgettable v.end, I would say, because nowadays we live in the lambda everything world. And if you have a more complicated lambda here, or maybe it's not a one-liner, maybe it's 2 or 3 lines, maybe it's a bit more convoluted, arguably, then maybe it shouldn't be a lambda if it's too long. But after all this weird shapely syntax with all the brackets and curlies and commas and semicolons, I would say it's almost an achievement if everyone all the time remembers to add the v.end there. So I would say it's a ticking bomb, and we should be lucky that we get it most of the time. And unfortunately, tooling cannot help you here, because your intent might be legitimate to just erase one element. So they clearly cannot distinguish this scenario. So you're forgetting that v.n there might be a recipe for disaster. And we did find such scenarios as well. And I think a better way to teach this before C++20 would be to clearly state the intention and call this on its right moniker, erase, remove, and, because this is the complete picture that people need to have in their head in terms of stuff that, or the ceremony that you need to go through to accomplish this kind of task. You have a remove, you have an end position, and then you have to come and tie it all together with an erase function. So erase, remove, end would be a more appropriate idiom. But that's not the end of the story, because the problem was so common that we finally fixed it in C++20, and there is an all-in-one solution, and that is we now have dedicated erase and erase if functions for list and vector, and these functions can operate. Basically, they combine the two operations together, and we supply them with the container directly and the predicate, and that's all. So it's certainly shorter. It is safer. I can't think of a way you can screw it up, and I think everyone should actually forget about the erase remove idiom starting with C++20. And I do recommend that you spread this knowledge. Surprisingly, few developers actually know about this addition to C++20. And that's the reason why I chose to do this presentation, so that people have a reference thing that they can share with their colleagues, to so that everyone knows that there is a safer way to leverage algorithms. And if you're in trouble, or if you suspect now after this presentation, if you suspect that you might have weird usages of erase remove in your code, I do recommend that you try to look up the erase remove pattern in your code, and you can do that fairly more complicated with maybe some regular expressions, or to be more precise, you could actually build an AST matcher and look for this pattern more accurately. If you're inclined to leverage libtooling to do such searches at scale in your code base. But I would say even something as basic as grepping for erase instances, or grepping for remove if instances in your code, I think will give you a sufficient pool of use cases to analyze, and you'll be surprised what you'll uncover. For a sufficiently large code base and a sufficiently long-lived product, you'll be surprised of the stuff you find in your code base, and you're probably going to uncover some obvious misuses, and definitely some head scratchers where you would have to figure out what the real intent of the user was there, in terms of what they meant to actually erase there, or to match for the predicate that they meant to write. So definitely worth doing this search in your code base. And if you're doing that, and if you can afford to upgrade to C++20, or maybe you're already there, if you did the search, you might as well do the replace and use erase if, which, mind you, is a global function in the std namespace, but that operates on vector, or list for that matter. And the short difference here, for list, there was a remove if member function before C++20. but that remove actually required that the predicate has the exact same type as the list elements. So it was not a heterogeneous lookup. Those new algorithms, erase if, that can operate on a list, can actually work with a heterogeneous argument for the lambda function. So if you can compare elements there, or you can convert elements to the type of the list, then it will work better. So definitely worth a search in your code base and a replace. So let's remove this erase remove idiom together for good. And with that, I inevitably reached the end, and I'll be more than happy to engage with you on Discord for the appropriate channel of this track, or even here if we have a bit of time. So feel free to reach out if you have comments or maybe your own experiences around this.